Here is the implementation of the queuing lock, or the so-called Anderson lock. The lock is an array, and the array elements have values haslock or must wait. Initially, the first element of the array has the value haslock, and all the other elements have the value must wait. Also part of the lock structure is a global variable QLast. To obtain a ticket into this queuing lock, a process must first perform a read and increment atomic operation. That will return the myPlace, so the index into that particular process into the queue. The process will then continue to spin on the corresponding element of the array as long as its values must wait. For the very first thread that arrives at this lock, the value of flags of 0 will be haslock, so that one will successfully acquire the lock and proceed in the critical section. Every subsequent thread, as long as the first thread is in the critical section, will come in, will get tickets that will point to some elements of the flags array that are from 0 to p-1, and they will not be able to proceed. Their value will be must wait. When the owner of the lock is done with the critical section, it will reset its element in the array to must wait in order to get this field ready for the next threads, next processes that try to acquire this lock. Notice that we're using some modulo math in order to wrap around this index, since read and increment will just continue increasing the value of QLast, whereas our array is of limited size. Releasing the lock means that we need to change the value of the next element in the array. So myPlace plus 1, we will change its value from must wait, it will become haslock. That means that that thread, that process will now come out of the spin loop that it's in. Notice that the atomic in this spin lock implementation involves a read and increment on a variable QLast. All of the spinning in this implementation happens on completely different variables, so the elements of the flags array. For this reason, issuing the atomic operation read and increment any kind of invalidation traffic is not going to concern any of the spinning that's happening on the elements of the flags array. These are two different memory locations, two different variables. From a latency perspective, this lock is not very efficient because it performs a more complex atomic operation, the read and increment. This read and increment operation takes more cycles than an atomic test and set. In addition, it needs to perform this modulo shift in order to find the right index into the array. And all of that needs to happen before it can determine whether or not it has to spin or be in the critical section. So the latency is not good. The delay is really good, however. When a lock is freed, the next processor to run is directly signaled by changing the value of its flag. Since we're spinning on different locations, we can afford to spin all the time, and therefore we can notice that the value has changed immediately. From a contention perspective, this lock is much better than any of the other alternatives that we discussed, since the atomic is only executed once up front and it's not part of the spinning code. Plus, the atomic instructions and the spinning are done on different variables, so the invalidations that are triggered by the atomic will not affect the processor's ability to spin on local caches. However, in order for us to achieve this, we have to make sure that first we have a cache-coherent architecture. If we don't have cache-coherent architecture, the spinning has to happen on potentially remote memory reference. Second, we also have to make sure that every element is on a separate cache line. Otherwise, when we change the value of one element of the array, we will invalidate the entire cache line, so we will invalidate potentially the caches of the other elements in the array, of the processors that are spinning on other elements. And that's clearly not something we want to achieve. To summarize, the benefits of this lock come from the fact that it addresses the key problem that we mentioned with the other spin lock implementations, in that everyone saw that the lock was free at the same time and everyone tried to acquire the lock at the same time. The queuing lock solves that problem. By having a separate, essentially a private lock in this array of locks, only one thread at a time sees that the lock is free and only one thread at a time attempts to acquire the lock.